I am Kim Hyung and I will be presenting this for this session. I am from Line, and today I'm with Line Plus Data and Machine Learning, and I'm going to talk to you about how to apply large ML for AI filter. I am an NLP engineer, and I am in charge of AI text filter model. I like to learn new technologies and apply them. I want to show you this picture. Um, it's a great picture that I drew. Well, actually, I did not draw this picture or I did not make this picture. This picture was created by AI. If you type beautiful forest, AI will understand my intentions and show me this picture. If you look at this picture, you can see that the AI is doing a better job, and this is because it is based on a large model. So the people who are listening to this session might be able to learn more about how to apply this AI filter in the large model. So my goal for this presentation is to show you how the large model can be applied to actual projects and how it can be used to solve problems. I'll move on to the main part of the presentation. So this is the content of my presentation. So I will talk about what AI text filter is and why we decided to use large model, what kind of issues led us to use large model, and I will talk about how to apply the model to improve the AI text filter. And lastly, I would like to share with you the experiment result and the expected effectiveness, and I will conclude my presentation. So this is the introduction part. First of all, I'm sure you're all wondering what AI text filter is. AI text filter is a filter that is included inside the monitoring system of Line. So if a user's text comes into the public service channel, and when it enters the Line monitoring system, we can tell whether it is a general sentence or not a general sentence. So non-general sentences will be categorized into personal information, sexual information, harassment, illegal information, or advertisement. And when we interpret these sentences, the monitors will be checking and dealing with these data. About 380 billion cases per month will be entered into the monitoring system. And so if the filter does not work well, the monitors will have to check more sentences. We therefore needed to improve the accuracy of the monitoring filter. So how did we improve the monitoring filter to increase accuracy? First of all, in order to improve the AI text filter model, we have to choose one model from the public pre-training model, which is written in a single language. And then we have to train the filter model according to the task. And out of the many public pre-training models, we do not know which model has the best performance. And when we change from existing language to other language, we do not know which model is the optimal model. So it requires overall a very high service cost. Therefore, in order to resolve this issue, we have looked at three solutions. First of all, when there's language change, what can we do? So we have expanded the model to support various languages. And because multiple language model has lower performance than single language model, we had to include large model. And why is the performance of large model better? Is because it uses the law of large scaling, and the size of the model increases according to the size of the data. And so the learning becomes continuous and the performance becomes better. So how can we train the large model? So we have adopted a training model specifically for training the large model. And we have applied these issues and resolutions to the AI text filter. The single language model that we're servicing right now has 110 million size parameter. We have expanded this to 11 billion multi-language model, which is 100 times bigger. We were able to reduce cost of development and service, and we can also expand to various languages because this is a multi-language model. Lastly, we have been able to adopt a training method for large model training. So what we want to contribute through this project is, number one, I want to introduce to you the technology used to train the large model, and we want to share this with you. And MLOps MLU team has cooperated with us in order to apply the large model to the AI text filter to improve the performance. And in addition to training the large model, we have also worked with the MLU serving team, which is in charge of the line ML service, to make better use of the model in the serving stage. Then, what kind of technologies can make good use of the large model? Let me talk a little bit about the different types of technologies. First of all, the large model can be dealt with in the scaling technology and also lightweight technology. So scaling technology makes full use of the large model as is, and it trains the technology in parallel. However, it requires a lot of computing resource. In terms of lightweight technology, it maintains the accuracy, but it also compresses the model. We need accuracy, so that is why we have chosen scaling. And now I would like to talk about scaling techniques one by one. First of all, this is the data parallelism technology. Data parallelism technology is a method that we use when there are many data, and at the same time, many data can be learned in the GPU in each model, and it has faster learning speed. Secondly, there is the model parallelism technique, and one of the most representative technologies is the intra-operator parallelism technology. In one layer, we will split the model parameters, and we train the GPU in parallel. And because we make use of the GPU in parallel, we can increase the efficiency. Lastly, for the final output, because the layer parameter is split into GPU, we use all reduce that combines all of these, and through GPU transmission, we can produce the output of the model result. Lastly, there is the CPU offload technique. So the model parameter is kept in the CPU space, and only when necessary it is used in the GPU space. So the model parameter can be used for training. And for large model, when we apply it to the AI text filter, we have used all three technologies. And there are other techniques that are required for training large model, but the problem is it requires a long time. Therefore, in order to improve the development speed, we have looked for a framework that can train the large model. We can train the GPT-3 model, and we can also use CPU offload in Deep Speed Framework. Deep Speed Framework is an open source technology, and it supports many technologies that allows training of the large model. So using Deep Speed, we were able to make use of large model quite in a fast manner. Now, I would like to talk about some of the work that we have done to apply large model to the AI text filter model. This is the overall flow diagram, and this is the deep speed framework that we have applied to our environment, and we have set up multi-nodes. For each node, there are 8 GPUs each. And during training, in order to make the test easier, we have defined the training configuration file, and we have made use of 11 billion multi-language model for public pre-training. And for each AI text filter task, we have done fine-tuning, and about 730,000 data were used for overall training. And let me talk about some of the difficulties that we have faced in large model training. So the first issue that we have experienced was setting the deep speed framework to fit our environment. And when designing the multi-node, the GPU acceleration file had to be shared. Thirdly, the public pre-training model code, if it is not parallelism phase or style, it was difficult to deal with the dependency issue in the fine-tuning stage. So let me talk about how we have dealt with these issues. So first of all, setting the deep speed framework in our environment was difficult because we had to deal with very complicated library dependency. And deep speed makes use of both CPU and GPU, and that is why it is very closely related to system library. And also in deep speed, there is a file that is created within deep speed called CUDA extension file for GPU acceleration. And the libraries required are G++ in deep speed, and also the Ninja build systems library version has to be in sync. So at the OS system level, we have first set up the library and then deep speed framework. And for multi-node, we have set up the library one by one. And because deep speed was used or could be used in the MLU environment, there are three strengths or merits. First of all, we can make use of all of the library that we have used for training. Secondly, we can make use of the more stable deep speed framework. Thirdly, we can use functions including Anaconda, which are supported by MLU. Lastly, we have created Docker image so that this can be used not only by us but also company-wide. We have also documented the entire setting process. Secondly, when MLU environment is set in the deep speed, when we provide training in the single node environment, we need to create the CUDA extension file for GPU acceleration. And based on the CUDA extension file, training can be accelerated. But how can the training be done in the multi-node environment? Well, when we expand it to multi-node, training begins at the header node, and when the work node receives the signal that the training has begun, the training begins in parallel. But when the header node, at the header node, CUDA expansion file is created, and it does not get sent to the multi-node. So if we simplify this problem, we can go into each server and create CUDA extension files so that people might think that this is a simple resolution. But as the number of worker nodes increase, this will become a very inefficient method. So in order to resolve this issue, we have created a file sharing module. So when the training begins, the CUDA extension file is made, and with this CUDA extension file, we refer to the worker node's IP address in the sharing module, And we created an automated system where the CUDA extension file could be sent to worker node automatically. So if you look at the overall picture, regardless of how many worker nodes had been added, at the header node when CUDA extension file is created, the sharing module shares the worker node with the worker node all the CUDA extension files so that multi-node training can be possible.
And moving on to the third issue, if the pre-training model code is not parallelized at the fine-tuning stage, there becomes the dependency issue where you cannot use parallelism. On the left-hand side, you can see the inter-operator parallelism. In this case, the model coding has to be done separately for parallelism. But generally, the public pre-training model that we use, in it, the parallelism code is not implemented. So at the fine-tuning stage, you cannot apply parallelism, and thus the dependency issue is rising. And in order to solve this at the fine-tuning stage, we created a converting algorithm that enables parallelism at public pre-training model. And the first is to enable parallelism of the public pre-training model code itself. And then if it is possible to parallelize the model's code, in order to load the code model, the public pre-training model parameter will be automatically partitioned with the algorithm that we implemented. And so the first point of resolution, in order to parallelize the model code, we have to know which part of the model needs to be parallelized. So generally, the public pre-training model is analyzed, and we try to find out the area where we could apply parallelism. And on the left-hand side, the general transformer structure is composed of encoder and decoder, and for each layer, the logic is mostly the same. So at each layer, we extracted areas that we could parallelize. The first was in the multi-head attention key query value, and secondly, the feed-forward network that calculates the multi-head attention output. And lastly, the intermediate feed-forward network that produces the final output. And the logics of these three layers were parallelized. So looking into detail, what we wanted to use was for the pre-training model, we implemented the model codes, the same logic, and at each model layer, when parallelism is applied, in order to give you an easy illustration, we set two GPUs, and we applied intra-operator parallelism that could have the GPU efficiently used. So as you can see in the bottom, in multi-head attention, key query value and feed-forward network was applied parallelism, and for residual connection, the parameters in each GPUs were all reduced. And in the intermediate feed-forward network, much like the previous case, after applying parallelism, all the final outputs were all reduced. And after all the output was done, it was feeding into the next layer input. And there's a need to converge the layers parallelism structure, and we refer to NVIDIA's Megatron ML paper to produce this structure, and I left you with the reference link that you can look up later. And what was interesting was in this experiment, depending on the model structure, the training speed and performance showed a lot of variability. So all in all, parallelism code design was very important. And after implementing the model parallelism, for the model parameters that are not parallelized, you have to partition and load the model accordingly. So for that part, you have to match the number of GPUs that use model parallelism and implement auto-partitioning. And lastly, you use the pre-training model that has parallelism, and you go ahead with fine-tuning. So to summarize all the processes, for the public pre-training model that is not parallelized, you need to convert to enable parallelism. And there is parallelism for the model code and partitioning for the model parameter so that you can upload the model. So as a result, even if the public pre-training model is not parallelized, you could use the parallelism converting algorithm to solve the dependency issue. And we analyzed the results of applying fine-tuning to model parallelism. And when you use this method, first to talk about the downside. For the public pre-training model that was not applied to parallelism, you enabled parallelism, and so the model convergence was unstable and the model performance was slightly down. But the benefit was, even if the public pre-training model code is not parallelized, you can do parallelism training at the fine-tuning stage. And so you can have the larger public pre-training models go through a learning process. And there's a trade-off between the benefit and the disadvantage, so you need further research on this methodology. And additionally, after applying the large model, we implemented the algorithm to enable performance tuning. And the algorithm was designed so that the label interdependence could be reflected. And in the algorithm, global correlation embedding layer was used so that when predicting the label, there could be a learning about the label's interdependencies. And so we were able to check the performance of the tuned model with the experiment results. And moving on to model serving. In order to do model serving, you need to optimize the model first. The smaller the model and higher the inference speed is better. Usually for a large model, when you're doing fine-tuning, the model parameter is reduced from FP32 to FP16. You reduce the parameter to perform training. And since the parameter is reduced to FP16, there is a likelihood that the performance will be lower. So to improve that, we applied the loss scaling technique to implement fine-tuning. And so the trained model compared to the pre-trained model, you could reduce the size of the model almost in half. And to optimize the inference speed, you do the kernel tuning to enable GPU calculation, and you should be able to process models as large as GPT, and that has the zero-shot task. And so you support parallelism at inference. And you take the optimized inference model and enable it to serve MLU serving platform. And the optimized part in inference is supported in deep speed framework. So that's why we use that. So the experiment result, I'd like to go over that with you. There are three models that we need to compare. One is the multi-language large model with tuned algorithm, multi-language large model without tuning, and lastly, the current AI text filter model in service. About 110,000 experiment data was used, and the data label distribution is skewed, as you can see from the graph, and that is the exact domain distribution of real data. And usually the data label number is much larger. The normal data label number is much larger than the non-normal data. And we see that the label is smaller for harassment and illegal. And we looked at the F1 score to compare the models when the label composition is skewed. Blue is large model tuned version, white bar non-tuned version, and gray bar the current model in service. Looking at the F1 score of the overall labels compared to the in-service model in all the large models, the labels show higher performance. And the tuned version has higher performance than the non-tuned version. And as for harassment and illegal labels, the large model model had a higher performance. And looking at the results, even if there is data imbalance, it's better for performance when you introduce a large model. And on the right-hand side, when you look at the overall average, large model with tuning had a 9.9% higher performance compared to the current model, and the non-tuned version had a lower performance by 1% compared to the tuned version. And let's look at the AUC score for model accuracy. The large model showed a higher performance compared to the current servicing model. And looking at the overall average compared to the service model, the current service model, the tuning model had a 9.1% higher performance, and it had 1% performance advantage over the non-tuned version. And we did some qualitative analysis of the model, and looking at the data used for the assessment, it is about extending loans to people who are financially difficult during the COVID pandemic. And so this content belongs to the illegal label category. And we need to have a good understanding for the model to understand what the sentence means. And under the current model in service, it predicts that it is illegal with a predictability of 12%. So the model does not understand this sentence very well. But if we introduce the large model with 99% accuracy, it predicts that this is illegal. And now, when we introduce the AI text filter to the large model in actual service, what are some of the expected benefits? So the expected benefits are as follows. When we introduce the large model, since it supports many languages, we can expand it to support multi-languages. And even if this is a multi-language model, it has a very good performance. And lastly, we do have the technology to enable the large model training. And as for the expected benefits on the service side, the AI text filter model had better performance, and so if we apply that to the monitoring system, we can have better performance. If there's a 10% higher performance compared to the previous AI text filter, the monitoring ratio falls by 0.3%. There are about 380 million data coming in every month. The previous model had a monitoring ratio of 1.5%. That meant they had to monitor 5.7 million data. But when you introduce a large model, the data to be monitored reduces to 4.56 million. So in conclusion, on a monthly basis, you can have reduced data to be monitored to 1.1 million. So based on this, we annualized the data to be monitored in a year. So compared to the current service model, when you introduce the large model, you can save to 13 million data to be monitored. So you can reduce 20% of the resources that you need to monitor in a year. And moving on to conclusion. So when you introduce the large model, there is a lot to be learned. One is in order to train and service the large model, there are many technologies required, and it was very difficult to understand it and apply all these technologies. But as much as they were difficult, it was quite interesting to apply to the large model, the AI text filter model, and to improve the performance. And I felt the importance of teamwork in introducing the large model, working with not just my team, but also with other teams. In the future work, it was difficult to tune the hyperparameter when we were doing the experiment. I think we need further research in how to effectively tune the hyperparameter going forward. Lastly, in my presentation, I could not explain MLU and MLU serving sufficiently. In the next section, Ms. Hyung Hong will talk about Line's end-to-end MLOps platform, and she's going to explain MLU and MLU serving in more detail. So please pay attention to her presentation. With that, I'd like to end. Thank you. Thank you very much. We will now move on to Plus Talk. We will invite the interviewer and we will have a in-depth discussion about the presentation. We'll take questions from the online audience as well. If you have a question, please use the question mark button on your screen. You can post your questions. Yes. From Yahoo, Shimizu Doru, from Yahoo Japan. Yes, I am Shimiz. For deep learning, we are doing similar things as was done by Mr. Hyung Kim. So in that regard, this was quite an interesting presentation. So I'd like to talk about what I felt listening to the presentation. When you increase the model parameters, people think that the performance goes up, but when you actually do it, it doesn't actually work that way. This is coming from my experience. But nonetheless, Mr. Kim, you solved the software issues and you were able to get a higher performance, up by 110%. And so moving on to my question. So 100 times more model parameters were trained. So was it all in one batch? Or was it 2 to 5 times to 10 times? Was there a gradual upgrade? So how did you actually do it?
Well, thank you very much for the question. It's a very important point that you made. Well, frankly speaking, it's not included in my presentation, but for us, we have increased the size little by little for model testing. So for instance, the final test is 11 billion, but in order to increase the model size to 11 billion, we first increased to 5 million, then 3 billion. So the model size was gradually increased. And when we actually did the testing, the model size continuously increased and the performance improved. The key of this is when we increase the model size, usually when we exceeded 3 billion, the accuracy and performance have increased exponentially. So that is something that we were able to confirm. I hope that answered your question. Thank you very much. And so increasing data and model size was 11 billion. So pre-learning data amount is something that I want to know, and I'm sure that people want to know about this as well. So how much data have you used for pre-learning? And I think it requires time as well. How much time was used for pre-learning process? Yes, to answer that question, in the case of pre-learning model, the publicly usable model was used. It was a multi-language model. And the training data, as far as I know, was about text data of 160 gigs. So that is my understanding.
Thank you very much. Yes, so that was a lot of data. One other thing I'm curious about is if the data is large, then it takes a lot of time probably for inference. So you did talk about parallelism, and could you give us a more detailed information? Was it a more real time, or did it take some time sequentially? Thank you for the question. First, at inference, we supported parallelism. Let's say for GPT, the model size is about 170 billion, and when the model gets bigger, the GPU memory for inferencing runs out. So we split that and we did parallelism. So that's one part of the question. And what was the other part of the question? Could you repeat? I forgot. Yes, it was about time, how much time it took. Was it real time? Because if it takes time, you cannot use it on a real time basis. What do you do it real time or was it offline batch type of work? Yes, thank you. As for real time usability, yes, we need more optimization if we want to use it real time. We can do batch type of data at this performance level now, but it's not that the inference speed is that much lower. So that's what I want to say at this point. Thank you very much. Yes, with that model size, real-time usage must be difficult. I think we can take that for granted. But I want to ask a follow-up question. For near real-time inference, the model that you used, and you could still keep the power of the model. And if you want to increase the speed, what are some of the possible approaches that you can take? Yes, first of all, I think there are many methodologies that we could use, but in order to keep the performance intact and to up the inference speed, looking at the recent research, there is a lot of parallelism involved and containerization, knowledge distillation. These could be some methods used. But according to the recent research, containerization is becoming more sophisticated so that there is 1% difference in performance, but the model size and inference speed could be reduced. And the second is for to implement the learning model optimized for GPU. So there are hardware technologies and then software technologies that we can use. Thank you.
Thank you very much. So when I heard that you can increase the inference speed, I want to look forward to what more developments that there can be made.